Most of the structural failures that people have blamed on concrete are not caused by concrete at all. They are caused by something invisible below your feet, groundwater. In today's video, I'm going to reveal to you the exact groundwater behavior responsible for the failure of these structures, and then the key engineering techniques you can use to fix them. I will also show you the common mistakes that engineers make while dealing with groundwater that can cost millions of dollars. Hello, my name is Carl. I'm a professional engineer, and for the last 9 years, I've designed and supervised hydraulic structures, and I've seen some of them fail due to groundwater. Let me tell you a short story about one of my earlier sites. 4 years ago, I was doing supervision on one of some medium-sized commercial building. It was a simple foundation. Everything was okay. Plant was fine. The soil test results were okay. Everything was perfectly fine. You know that feeling when the site is too quiet and nice and then you feel like God is the one doing the supervision? Yes, it was that kind of a vibe. Even the client came to me and said, "Engineer, this is quality. This will outlive me." I laughed. Big mistake. Because 2 days after that, something really happened that made my stomach pop. Just next to the foundation, the soil had slumped by about 10 centimeters. No range, no poor workmanship, no problem with the foundation. Concrete was perfect. It was groundwater. It just sieved through and we never managed to detect it. We had to redo that section of the foundation, redesign the drainage system, and delay the project by about 3 weeks. Now from there I learned that groundwater doesn't need to be visible. It just needs a path. Most people think groundwater is just water underground. Wrong. Groundwater, it is the pressurized water which moves below your feet, and it has a lot of impact and damages it can cause. It is the culprit responsible for flooding of dams, flooding of culverts, water through retaining walls. Surface water is like a river. Groundwater is a river that you don't see but comes with a lot of destruction and impact. This takes us to another part of the video, the dangerous behaviors of groundwater that engineers rarely talk about. There are basically 4 major groundwater behaviors that engineers ignore, and they have a lot of impact on our structures. The first one is uplift pressure. I normally call it the silent jack. Have you ever seen a car being jacked? Yes, groundwater can do the same to structures. There was a water tank project. Due to the need for maintenance, the contractor had to empty the tank in the night to do the routine maintenance. But the next morning, the tank was just above the ground. It was pushed out by groundwater. Imagine just waking up and then you find your tank up in the sky like it's going to heaven. That's groundwater. That's not bad concrete. It's groundwater because the uplift pressure was greater than the weight of the structure. The second one is a seepage or piping. I call it the soil thief. Seepage doesn't just move water, it carries soil too, stealing the soil. When any soil that is below the structure is swept away by groundwater, the structure becomes useless because it has no foundation where the oil weight will be anchored into. This can be commonly seen using one of the models I generated using a GeoStudio software, where you can see how water part is moving along the embankment and the oil channel in terms of the flow net to a point at the downstream side. So which means soil around this section is going to be swept out by the groundwater force and taken to the downstream side of the reservoir. How soon we are going to learn how to handle such a problem. The third one is being the water table rise. I call it the seasonal assassin. Most contractors, they build like the water table stays constant. Groundwater levels rise when the land is developed, during rain, and when drainage paths are blocked. I saw a house extension crack in under 90 days because it was built on an old natural groundwater flow path. This water table rose and the foundation behaved like it was built on jelly. Again, not concrete failure, but groundwater behavior. The last one being groundwater flow path. I call it the invisible highway under your structure. And now this is the one which is most underestimated by a lot of people. Water doesn't move randomly. It follows a flow path. It's natural underground channels. And your structures become the obstruction. When you build a foundation, you interrupt the flow path of the groundwater. So water responds by building up pressure around that point, and then it causes impact on that very structure. This is why a structure can still fail. Even if the concrete is perfect, the steel work was well done, but groundwater impact was not factored for in your plan. So why does concrete always take the blame? Concrete takes the blame because we normally see cracks, settlement, tilting, leaking walls, and damaged floors. Then we blame it on concrete, contractor, and poor workmanship. But the invisible force for the fall of the structure is normally seepage, piping, uplift pressure, and pressure under the slabs. Structures rarely fail from the top. They fail from below, where most people never look. I've seen this firsthand on dams, spillways, retaining walls, culverts, and many other structures. Let's see how to control groundwater. Now you can't stop groundwater, but you can control it by seeing how to direct the flow. One of the best ways you can use to control groundwater is by providing a drainage path. Things like French drains, gravel layers, perforated pipes, and subsoil drains, they serve one purpose: to give a flow path for water to be channeled through. We design the drains by performing a geotechnical investigation, normally called SIF analysis, whereby we analyze the size of the base soil which is surrounding that drain. This is normally achieved by a simple equation which states that the maximum size of the perforation should be less or equal to D50. D50 is the grain size of the soil at the 50% finer. It is achieved through the same test. Now, the motive of this perforation is to make sure that hydraulic conductivity is achieved. That is, water is able to pass through the perforation. At the same time, the base soil or the soil within that section should be retained and should not be able to pass through the pipe. But the second method is achieved by using relief pressure. Weep holes, drainage blankets, and pressure relief pipes allow groundwater to escape. When water is allowed to escape, the pressure drops down and the structure is protected from damages. This uses the same design as we previously looked at, whereby the maximum perforation size is greater or equal to D50. Next is by using filter material. The filter material prevents soil from being washed away, and at the same time, it allows water to be drained through that section. So the filter is normally designed by doing sieve analysis. The design is adopted using the Zagis criteria, where it looks at the soil retention and hydraulic conductivity. Using this equation, D15D over D85F should be less than 5. That is to ensure particle migration. And then for hydraulic conductivity, to allow water to flow, it is D15D over D15F should be greater than 5. So using those two equations, we can commonly achieve that in the laboratory. And this is the same method they use to design filter in embankment dams. The fourth method is by using cut-off walls. Cut-off walls are barriers that go deep into the ground to block the seepage. They don't stop water completely, but they prolong the length of the water flow and therefore shorten its impact. This process helps to reduce the pressure. You normally see them in dams, spillways, culverts, and some other structures. The basic rule for determining the depth of the cut-off wall is to make sure it is anchored into a stable foundation ground, if not at least 0.75 times the height of the dam. Let me show you an example. This is one of the models that I performed to determine the depth of the cut-off walls. In hydraulic structures like a dam, spillway, cut-off walls can be put both upstream and downstream, and sometimes they can also be put in the middle of the structure. The basic rule of design of these cut-off walls are the depth of cut-off wall upstream equals to the full supply depth at the upstream side divided by 3. Then at the downstream side, it is the full supply depth at the downstream side divided by 2. I promised to give you the one common mistake that people make while dealing with groundwater. Most people think waterproofing membrane solves the problem of groundwater, which is very, very wrong. Waterproofing membranes keep water out. It does not stop water pressure from building up. The pressure will still find its way to lift, push, crack, and even seep through the structure. Groundwater doesn't respect membranes. It respects pressure relief. So don't think waterproofing is enough. Groundwater destroys structures silently, but not all failures are caused by groundwater alone. Others happen because the engineers failed to anticipate them. In the next video, I will reveal how engineers, not rain, destroy roads and the best ways you can use to fix this problem so that lives are not lost.